We're going to be talking about local attachments and spot welds. But before we get into the content, I just wanted to kind of look at our schedule coming up here, and mainly because we have the first exam coming up. So these dates that you see here should be exactly the same as the published course calendar, and want to make sure that you're adding one day for the distance dates. And what we want to do is kind of focus on this right here. Exam 1, 80 minutes long. We'll be covering lectures 1 through 10. So this is lecture 10 today, so everything up to and including today's material. So just to give you a feel for what the exam will be like, first of all, it will be open books, and the lecture notes are available. Using a laptop is fine to access the notes or do calculations. You will not need the GAS software, so you don't have to worry about that. As to the kind of exam it will be, the kind of questions, there'll be several application calculation type problems, very similar to the homework or to the examples that I've done in class. There may be a simple derivation type problem. And again, it won't be intense. It'll be a pretty straightforward one, and there'll be some kind of design judgment type questions, like which would be the better configuration for a structure. Questions like that. How would you improve this structure? So that would be like a short sentence answer or a phrase. So particularly for the distance students, make sure that your proctor is lined up. You want to do that right away so that you're not struggling with that at the last minute. The way the process works is that a PDF of the exam will be sent to the proctor. They will print out the exam, so you'll receive an electronic copy. You'll just receive the printout. You will do your fill in the exam right on the paper that you'll be given. The proctor does not have to be in the room with you, but they'll pop in at the end of the 80 minutes and then collect your papers. They will scan it and then return the completed exam back to the university here. Okay. So just so there's no last minute confusion, the date of the exam for distance students, a 1 day delay, so that would put it at June 20th for this first one. And if you have any questions on this, please email me, and we'll try to get them straightened out. But for now, we still have a few weeks, so this would be the main action item here. Was just be very confident that your proctor is lined up, and your proctor will be around on June 20th and probably the day before and after, and that they won't be going on vacation when this all occurs. Okay. So let's get on to the content for today. Again, what we had been doing was looking at, in the context of beams, we've been looking at the kind of classical equations initially for beam behavior, and then we've been looking at the differences for automotive sections. So non-symmetrical, they tend to twist, they're very thin walls, so plate buckling is a big issue. And now we want to look at a couple of more. And that's one is that they're generally made up of several pieces. They're not just a monolithic section like the I-beam. So we're going to need to weld some pieces together, and those welds will affect the performance of the section. And then finally, in today's lecture, we'll also be looking at the fact that our sections are often loaded at a particular point, and that causes some issues for thin wall structures. Okay, so what we're going to be looking at first is this idea of welding the structure together, and what does that do to the performance. Okay. So if you want to think in terms of physical terms, basically we're going to be looking at spot welds as a main method of fastening the parts of a structure together, and then secondarily, from the point of applying a point load to the structure, is basically the topic of well-designed brackets. Okay. So the idea of resistance spot welding is used for automotive construction, and here we're seeing a framing station where the sides, top and the bottom of the car comes together, and you see a lot of the robotic spot welders pulling that all together. The reason spot welds are used are primarily they are a high production rate process. There's no filler required as it would be in arc welding, for example. And also the process accommodates some variability in the fit up. So the spot weld process kind of pulls the two parts together if there's a little bit of variation in it. So let's take a look at what the spot welding physics are. So this is just to give us a general idea of what's important in spot welding. It's not to get deep into this particular process. But the elements are, we have a couple of arms, there's electrodes involved. We pass an electric current through the arms, through the electrodes, and that causes the metal essentially to melt. And it melts as these arms are clamped together rigidly. So here is a little picture of where all the action happens right at the, it's called the fang surface. So that is, here's our two pieces of metal that we're welding together. The interface between those two is called the fang surface. Here we have the electrodes. Electrodes are generally copper. So we have a stack up here. We're looking at the electrical resistance as the sum of all these elements. And the power, which is really the heat, is proportional to the current squared times the resistance. So we want to make sure that the maximum power is being dissipated right at the fang surface. So we want that to be the resistance that where the most power is. So this is basically how the process works. For structural purposes, we're not going to get too involved with this. Sometimes for aluminum welding, we can actually get a higher resistance, not at the fang surface. Remember, we want that resistance to be located where we want to melt the parent metal between the two plates. If one of the resistances, for example, between the sheet and electrode is greater than at the fang surface, then what we end up doing is welding the sheet to the electrode rather than the two sheets together. So that's why this is of some general interest. Okay? Generally for steel, that is not an issue. So there's a few other types of welding. Here's a press welder. Here we have one of the electrodes is actually the fixture. So if we look at this little picture here of two door frames being welded together, here we have a fixed electrode that's part of the fixture. It doesn't move up and down. The workpiece is put into this fixture, and then a moving electrode comes down and makes the weld. And in a press welder, generally there's several spot welds that are made simultaneously. The principles are all the same, though. Very infrequently, we can have something called a single-sided weld. That's where we only have one electrode. So this happens maybe when we have a hydroform tube part, which has got a considerable wall thickness, so it's fairly rigid. That's put into some fixture here that holds it up. This is grounded for the electrical connection, and then the electrode comes down and makes a weld there. And of course, the distortion of the part is a big issue here. There's many other fastening processes that we won't get a chance to talk about. Another is stir spot welding. So we have a little spinning element here that just basically creates friction at the interface and creates the heat to melt the metal in that way. So electricity is not involved in this one directly. Okay? So what we're going to be focused on again is a traditional spot welding, and what does it do from the context of body structure. So these are all things that it does. It provides some additional geometrical constraints that we can't shape our sections maybe exactly like would want to, because we have to have access for spot welders. There is a very severe stress concentration that's introduced at each of the spot welds. This results in fatigue life reduction right at the welds. Also results in a stiffness reduction, and we're going to be looking at this in some detail. There's also an additional buckling mode beyond what we've looked at so far, kind of a between the spot welds buckling mode. So what we're going to do is just kind of very quickly take each one of these factors and describe what we're talking about. So the first one, geometrical constraints. And this is, I think, pretty straightforward to understand. We have some welding tips and welding electrodes, and we just have to make sure that we have space to accommodate those. So here's an example of good accessibility to the flange. Here's an example where we kind of have shaped our part such that it would intrude on those spot weld tips, so that we can't really get in there with the spot weld tips to make the weld. Okay, so that's basically what we're talking about there. So how much space do we actually need for the flange? So here's the minimum flange length, somewhere between 14 to 17 millimeters, and this depends on the greatest metal thickness. So if we're welding more than 2 metal thicknesses, what one is governing this equation is whatever one is the thickest. So we said that there's a stress concentration at a spot weld. So here we're considering just 2 strips of material with 1 single spot weld here. And we're pulling them with a tensile load. And this tensile load is lined up with this top sheet in the center. And this reaction force is lined up with the bottom sheet. And if we enlarge this area here, so we're making the thickness look really thick, we can kind of see that the loads aren't in line. So we have a axis for this top load and a axis for the bottom load, and they're offset by about the metal thickness, right? Half a T here and half of a T here. And when we pull on this, it distorts this little specimen like you see there. And in distorting it, it makes some very high stress concentrations right at the leading edge of the spot weld. So if we kind of look at this in the top view down here, we see this exploded view right here. So here, when we're far away from the spot weld, we have a uniform stress distribution here. Sigma kind of median is what we're talking about. And then here we're showing lines of ratio of the stress at a particular location divided by that average stress. And you can see it gets very large right at that this leading edge of the spot weld, over 10 times the median stress. Okay, so this can be a problem, particularly for fatigue. And if we look at the SN curve here, so this is the stress or load level. This is the number of cycles to failure. If we were to consider just a base material, so right now we don't have a spot weld in it, so we would have this kind of a behavior in an endurance limit. And now if we take that same little specimen, about 1 inch wide, you can see it here, and we do a cycles to failure curve here, we've really dropped down a huge amount. So this is where that factor of 10 or so that we looked at before comes into play, that the actual stress distribution where this little joint is going to fail is actually stressed 10 times more than at the nominal value. So that'd be right here and right there. So what are some ways to mitigate this? One is to use weld bonding. In weld bonding, we put a layer of adhesive down between the 2 surfaces, and then we put a spot weld in it. And that bonding or adhesive tends to distribute the stresses much better, so you see much less degradation in this welded joint, but still considerable. What we're showing here is several different conditions for the steel, the mild, high strength, and galvanized. But the message is that all of them have this pretty large degradation in performance. And this is just the way it is. If we look at a strength kind of a load, so now we're looking at a single load application, and here we're looking at the shear. This is a lap shear condition, a single load. So here we're looking at what is the load that we can apply here before we start to tear the spot weld out. And here we're looking at the thickness of the thinnest sheet in this case. So here's our kind of a typical range, a little bit less than 1 millimeter up to a little less than 2 millimeters. So we can see what the load carrying capacity is, again, of a single spot weld to get some feel for that. So this is the shear case that we're looking at here. You can kind of get that idea. If we kind of drew this like this and this, we're kind of shearing the spot weld. Another kind of a weld, also a spot weld, is called a coach joint, or the joint is in peel. So you can kind of imagine that as we pull up on the metal here, we're trying to kind of pull this away like this. We're kind of peeling the spot weld. And this performs much, much, much worse than this other case. So here is the maximum load that we can carry. The x-axis is a different variable. It's the offset distance. So how far are we from where we're applying the loads? This is the surface we're applying the loads right here to where is the spot welds. And as you can imagine, the farther away we are, the more we're getting this peel effect. But one of the things I wanted to note is the difference in the magnitude of the variables. So this is 300 newtons. That would correspond way down here on this chart. So you see that welds in peel are much worse performing than welds in shear. So this is one of the very important principles in designing a structure that's going to be spot welded together, is to try to get those joints in shear. And we'll be looking at some physical ways to do that a little bit later on. Here's another way to kind of visualize the same data. We're still plotting the peak load, and now along the x-axis are different types of steel grades. So here is the shear test, and here's the peel. And again, you can see the dramatic difference in each case. So this is what we always wanted to design for if we can. So let's look at a few physical structures to see how we can get this condition, not in a simple lap test here, but in the real world parts. So here we're looking at the rear compartment pan. We're saying it's made of a couple of pieces. One is a region here, it's pretty flat here, the outside, and then the other is this deep dish. And often this is two pieces. It's very hard to stamp this part as one piece. So typically the pan is made separate, and then that's welded in to this little flat area here. So here you see this is the equivalent of the yellow area above from here to here, and this little flat area here is represented by these. Okay. So in this first illustration on the left, this is a joint that's subject to peel. It's called a coach joint. And whenever we visualize the loads on sheet metal, we always visualize them as in the plane of the metal. Remember in the last lecture we talked about how advantageous it is to try to put the metal in membrane-like loadings rather than bending. So here's the loading condition, and you can see that we're trying to peel those joints apart. Okay, that would be under a downward load here. So we don't want to do this. So how would we make this into more like a tensile condition? We could do something like this here. And now when we look at this little joint area, we literally have a shear type joint. Okay, much better. Okay, so why would you ever do the one on the left? Well, when you think about it, in the manufacturing plant, we have to have nice access to these welds. We want to have small arms on the welders just for their own rigidity, and to reduce the mass on the end of the robotic arm. So when you think about it, these arms can be pretty small, very accessible to get into this area. So that's one reason why this might be desirable, not from a structural standpoint, but from a business standpoint. In this case, the arms would have to be, fairly large to kind of go around whatever other parts are in the way there. Let's take another example here. Now we're looking at the strut tower on the car, and we're taking a section of that. So here's the upper rail. So that would be this part here. This is the mid rail down here. So that would be this part here. And then here we're looking at the strut tower itself. Okay. And the main load that occurs on the strut tower is a big axial force right down the axis of the shock absorber. And again, if you can imagine this joint here, let's draw it like this. Here we're applying a load here, and we're trying to peel it away again. So this is a peel joint, not so good. Let's look at this one down here, though, and that's looking like this. We're applying a force here. Here we have another metal here. So we're applying a force there. So this is this is in shear. So that's good. Okay, so we got a good one and we got a bad one. So how can we make the one in peel a little bit better? One is we can change the configuration like this. We can kind of rock the flange downwards, and now when we apply a load here and here, we're in shear. Okay? And again, we have this trade-off between weld accessibility and structural performance. So when we consider this one, it's really easy to get the weld tips in there. When we look at this one, the weld tips would have to be much larger to get around this upper rail. Okay, so this is kind of showing what we have to contend with is getting a room for those spot weld tips, good accessibility for those. So it's good to know what does a structure, what's really best for the structure, and then we know when we're making a compromise if we have to make it. So here's another example. Here we're looking at a cross member to rocker joint. So here's the rocker. Here's the cross member. And we're looking at this joint in out of plane bending. Remember when we talked about that? So here we have some spot welds up here. So we can imagine when we're applying a moment like this, now we're looking at a section right through here, that we have a tensile load here and a compressive load here, and here we're trying to put that into peel. So how can we improve that? Here's one way to do that, and that requires some shape changes on the rocker inner, and this doesn't get pure tension. If we wanted pure tension, this would have to look like that. Okay, and if that's a viable solution and the geometry works, then that's kind of the way we would want to do it. So let me make this a little bigger. That got to be pretty sloppy drawing. So like that. That would be in pure shear. Okay, so this idea of designing for shear is definitely what we want to do. It has much better strength performance. But we're not all there. I mean, shear isn't ideal because we have to have some additional deformations in the structure that we also have to contend with. So let's take a look at what those are. So this represents a huge enlargement of the shear joint. So we have two pieces of metal that we've welded together, the blue one and the pink one, and we're applying a load essentially down the center line of each of the thicknesses of metal. So we have an offset here between this load and this load. And what that offset does is it causes this joint to deform. And right now we're concentrating on the elastic deformations. We're not pulling this thing so hard that we're gonna tear the spot weld. So we're going to get some deformation that looks like this. And the harder we pull it, the more little rotation that we're going to get here. And as we rotate here, we move a little bit here. And that means we move a little bit here. It's a little bit out of proportion. We move a little bit here, and we move some there. Okay, so we're getting some additional deformations that we hadn't really anticipated, even in the elastic range. Okay, so we're getting this rotation and this movement here and this movement here. Okay, so again, the rotation of the spot welds causes longitudinal deflections at the flange. So that's this and this and this and this. Okay, so the flange is kind of moving against itself. So it adds an additional flexibility into our structure that we didn't know we had. So I'm going to show this now. We've been considering just one spot weld. So here's just an example. Now we have a flange that has a row of spot welds. We're just going to look at 3 here. And it basically has the same behavior. And just to try to convince you of that, here we made a little model of this joint. So we have a little piece of plastic here, which represents the center line of that top piece of metal. We have another one here that represents the center line of the bottom piece of metal. And then we have some offsets here that represents the distance between the two. Okay? And we've exaggerated all of those in this little video that you're going to see. And what I'm going to do in the video is I'm going to pull, just as we're showing here, and pull in this direction. And you'll see these rotate, and you'll see that the flange actually moves across itself. It kind of shears. So let's see if we can play this video. Okay, so you can imagine a whole long flange with 10, 12 spot welds along the length of a beam undergoing this kind of a shearing deformation. Okay. And we can do some calculations on this. We can actually go through this. What if we know the properties of the two pieces of metal that we're welding together, and we know some of the dimensions, like the width of the flange, what's the pitch of the spot welds, the distance between them, and then just how long is the flange, the thickness of this. And we're assuming that the thickness in this case, it's the same for both upper and lower. And then what we want to do is relate the force to the amount of deformation in this direction, and express that as a stiffness. Okay? Now in the textbook it develops this equation. You won't be responsible for that development, but you can kind of see the important parameters that, as we would expect in any kind of a stiffness problem, Young's modulus is involved. Kind of the area of the flange. So the higher that is, the kind of the stiffer the flange itself. The pitch squared, so it's very sensitive to pitch, and it's in the denominator, so that the larger the pitch, the lower the stiffness will be, or the more flexible the joints will be. Okay, so this is a stiffness that really we hadn't anticipated. We haven't really talked about it because up to now we've been considering our beams to be kind of monolithic, that they really don't have multiple parts that are spot welded together. So let's kind of look at the implications of this. And now we have this flexible welded joint in our beams that we didn't know we had. So how are we going to kind of model for that? So what I'm going to show you here is a beam that we would normally we would say, well, the beam is going to be welded together here and here. So effectively, in what we've looked at before, we wouldn't even show the spot welds, right? We would just have something like this. And if we're twisting it, in this case, we're going to apply a torque here and here. And what we're going to show is what is the motion that this row of spot welds is really restraining. Okay, so what this little model does is it has a spot weld on one side, but it doesn't have one on the other side. And what I'm going to do is twist this, and I'll put a little tick mark on the top and then a dash line on the bottom. And as I twist this, you'll see how these move relative to one another, right? Initially, they're on top of one another, but once I start twisting, they move. So what we're going to be looking at is the shearing deformation. You can see how they move relative to another. Now imagine a spot weld clamping the dash line to the solid line in each case. Okay? So before this talk, in the last few slides that I've showed you, we would have thought, well, once you put the spot weld there, those two, the dashed and the solid lines, are kind of rigidly fixed together and they don't move anymore. But now we know that's not true, that there is some flexibility. And just to make sure that we're all on the same page, let me illustrate that here. We're going to look at a little different shape here. So it's this funny, odd shape here with a blue flange and a red flange. So that's represented here and here. And again, we're going to be twisting this. And we kind of looked at this before when we were looking at the sections under torsion and developing the equations for them. But now we're going to be considering this idea of spot welds. So again, here we know what's happening, that we've opened the section. And because it's open, we get the idea of warping here. Okay? So there's some movement here between the top flange and the bottom flange. Okay? So now we're going to say, aha, well, we're going to make this a closed section by adding a spot weld. Okay? And again, ideally that spot weld clamps those two flanges together so we have a perfectly closed section. Okay? But we really don't. We know that every time we have a spot weld, we have some flexibility there because as we pull here and here, this rotates and then this moves a little bit. Okay? So really we're not putting a perfect connection there, we're essentially putting a little spring in each place. So if we can imagine this connection to look something like this, so our little spring goes between the blue dot and the red dot. Okay? And if we were to be able to draw this right, the blue and the red dot would be almost right on top of one another with a little spring connecting them. Okay? And we know that spring rate is due to the fact that we have a spot welded joint there. So now what's going to happen is that as we apply our twist, we really don't have a completely closed section like we thought we did. We're still going to get a little bit of warping. It's reduced, but not totally eliminated. Okay, so we're not fully at the case where we have a closed section. So we're kind of somewhere in between. And the reason we're somewhere in between is we have the spot weld that has a little bit of flexibility where we're attaching it. And the question, of course, is, well, is that a big flexibility or is that a little flexibility? Is it closer to the ideal closed section or is it closer to the open section? Okay. So here is some calculations that shows where that ends up being. And what we're plotting here, we have this odd shape here. Okay, this would never really make a structure that looks like this, but it's a structure that's been bent back on itself like this. So somehow we were able to form that. And then we're going to just put a spot weld there, just so we're looking at one spot weld flange rather than two on each side. Okay. And here's the dimensions that we've taken for this shape. And what we're plotting in this diagram is the true or the effective stiffness of this with a real spot weld that has some flexibility, like we just looked at a few slides before. And we're going to divide that by what is the ideal stiffness, and that would be what if this was perfectly a closed section. Okay? We know the calculation formulas for that. So how far would that go? If this spot weld behaves exactly as a rigid member there, then we would get a value of 1 for that. If it acts very flexible, then we'll get something less than 1. Okay? And along the x-axis is the spot weld pitch. So this is how far are the spot welds. If we look at this long flange, these are uniformly spaced, and that distance is p. So that's the spot weld pitch. Okay? And as we would expect when we have zero pitch, that's as if we would have welded this all along the side. So it turns it into a closed shape. So that's why we have 100% effectiveness or 1 here for this ratio. And as the spout weld pitch increases, as the spout welds get farther and farther apart, this curve goes down. And way over here, what is that, maybe 85 or so, we're down to about 75% of the stiffness we thought we had when we welded this thing to the ideal closed section. Okay? But where do real spout welds fall? Here is kind of the range from 30 millimeters between the spout welds up to a little over 50. So this is the amount of degradation that we can achieve. Okay? So it's somewhere, it's not trivial, it is a number, it's around 90%. So we've lost essentially 10% of the rigidity of this when we thought we closed the section because we're using spout welds to close it rather than some other method. Okay, so this is just the significance, and again, this has been fairly qualitative. We know that it's a function of spout weld pitch. We know that it is an important number, that it's not like 99% effective. It's something a lot less than that, 90%. Okay, so how do we really verify something like this? We had a really nice opportunity to do that some years ago. One of the minivans in production had a spout weld space frame. So it was basically a bunch of beams that were spout welded together, and then the surface of the car was composite panels that were glued to it. Okay? But we're just considering the space frame here made of spout welded metal, spout welded steel. And the way they did their corrosion protection was to zinc dip it. So they welded all these beams together, and then they zinc dipped the whole car afterwards in a molten bath of zinc, like you see here. And then that was the body in white for the particular car. So what we did was we got a vehicle before dipping. Okay, so that had the flexible spout welds phenomena that we talked about. Okay, so this would be less than 100% efficient. And then we got body in white after zinc dipping, and we did some torsion tests on each one of these. So after the structure was dipped in the zinc bath, it essentially forms a closed section here. So we had the ability to compare the results of several bodies, both before dipping and after. And indeed, we found that this was about a factor of 10%. So once it was in the zinc bath, it was 10% stiffer than before it had been put through. And that's this phenomena of the spout weld flexibility. Okay. So let's look at another phenomenon. We've already gone through a few. One is we have much lower fatigue life when at the spout weld, so we have to account for that. We had lower strength whenever we have a coach joint rather than a shear joint. And even when we have a shear joint, we have this additional flexibility occurring in the spout welds. Okay? And another phenomenon that we have is an additional buckling load here. And this is really kind of between the spout weld buckling. So it's kind of like a pucker of each of these little plates acting independently of one another. Before, when we looked at the compressive loading of the flange, we were looking at these behaving in concert with one another, buckling kind of together to the right or to the left. And now we're looking at each of these plates buckling independently. Okay? And the boundary conditions look like this. So we actually have a fixed condition. I said that's always hard to come by, but in this case we can achieve it, simply supported on the bottom and free here. And here the length of the little plate is the spout weld pitch. So here we have half a spout weld and the other half. And the reason we can get this fixed condition is that actually if we looked at this, say here's another spout weld here, that this would also be buckling like this. Okay, so that's why we why this behaves as a fixed condition, because there's no change in the slope at that particular point. So I have a little animation of this, or a video here. We'll be able to look at the top flange right about where I'm pointing right now, and we'll see that. There we go, right there. So you see there, the two little flanges are working independently of one another, and we have no change in slope at either end of that little plate. So what we need for this condition is a buckling coefficient. We use the same equation as before. And again, the geometry forces the slope to 0 here. The A value is the pitch. So that's the distance between the spot welds, and B is the flange height. So the bigger the flange, the smaller this A over B ratio will be. Okay, and this is the value for the buckling stress, or the buckling coefficient, excuse me. Okay, so I think we've covered what we want to go through for welded joints. And again, we talked about this in very qualitative terms, not a lot of equations that we can really use. So this is just more importantly, just good design direction, good design practice. So now we're going to look at another phenomena here for thin-walled sections, in that we generally will load them at a point. So what do we mean by that? Basically, it's how do we design brackets to apply a point load to this thin wall section. Okay. So why is this important? So let's take a look at a rocker section, and we've kind of extracted this from the car, and we're going to pretend like this is loaded as a cantilever beam. So we're holding one end of this rocker, and we're pushing downwards on the other end, just like a cantilever beam. And from the material we covered in the first few sessions, we came up with a deflection formula for beams, cantilever beams, that look something like this. And we would expect the shape of this beam to deflect something like that. So here we're going to have an animation here. So here is the grounded portion of this structure, and here's where we're going to be applying our load. And we would expect it to kind of deform, just like I showed you when we talked about our cantilever beams and beam buckling, or beam deformation. Okay, so let's kind of look at how this actually deforms. And I play this video. So again, we're applying a load here at the tip, and we're not seeing anything that looks like beam behavior here. We are seeing a lot of distorting of the section. Let me play that one time. Look at the section shape at the beginning here, and then the section shape as we get near the end of this, right? We're kind of smushing the section. And that's kind of a consequence. We have thin wall structures, so they're somewhat fragile when we go in and put up a point load on them. So this is kind of what I was trying to indicate here, is the initial shape here, and then the dashed line is the final shape. And we never really did see this thing deflecting like a beam, right? So our model is only partially adequate, right? We have to take into account this deformation under a point load. So again, this is what I meant by a point load, if I wasn't perfectly clear before. So let's kind of look at how this works in a real design situation. So here's a little cross member in a hatchback car. This is at the hatch opening, and we're going to mount the latch at that point. And we have some requirements for this. We want the stiffness at that point where the latch applies a load to be 1,500 newtons per millimeter. And we're going to treat this as a simply supported beam. So we have some joint at either end, not a very good joint. So these are simply supported. And we have a section here, 100 millimeter square. Here's a thickness of 0.8. So we have a thin walled section of steel. So we have our beam equations. So here's this case here, kind of turned on its side. Here's the relationship. and we just plug in our values. Here's the moment of inertia, the B and the H here, 100, and the thickness 0.8, and then the H and the B again. And we get a moment of inertia value and plug them into our beam equation. Here's Young's modulus for steel, moment of inertia, and then the cube of the length, and we get a value of 1570. And we compare that to our requirement and say, well, looks like we're good. Is it okay? And in reality, even though our first order calculations look okay, in reality, if we tested this structure, would get a value of about 30 newtons per millimeter. So orders of magnitude off from what we expected. And the reason for this is like we saw in the little cantilever shape, is that we're going to get a lot of distortion right at the point of load application, over and above the beam deformation. So here's maybe that section that we were talking about. This is not quite square, but here's the thin wall section, and we're applying a point load, and we would get a lot of distortion right at that point of load application. Okay? And what we really want to do is something more like this case, where this is the same picture where we've kind of moved the load to the side, and we've tried to load it as a shear load into this red wall. Okay? This would be a much more rigid way to load the beam. Okay? So what I'm going to show you is a little video again of this case. The first case in the point of load application isn't quite a point. It's my finger pushing down. So we're going to see this case first, and you'll see a lot of deformation of the section. And then we're going to see this case next. And I'm actually pushing harder when we're looking at this case, and you'll be seeing much, much less deformation. So let's just see this. So you see a lot of the distortion. The walls are kind of buckling, and here I'm pushing much harder along that shear wall. So this starts to show some of the principles that we want to try to apply to our section. We have to modify it just a little bit in order to apply these loads in a way that we're not distorting the section too much, right? We're creating this big, nice beam that we want, and then we're kind of giving it all away by having a lot of deformation very locally, okay? So we want to find out how can we make this very stiff so that we gain the benefit of having a nice big beam like this. So how do we kind of visualize this? And again, this is going to be one of those derivations where you just want to follow the thought process rather than getting involved too much in the mathematics here. So what we're going to do is say we're going to take an assumed deformation. We saw just by looking at it that it's kind of a half sine wave here. We have a point of load application, and the whole section distorts a little bit around that point, and that's what we're trying to model. And what we're going to assume is that we can kind of take our beam and kind of slice it like a loaf of bread. So here is a slice, and it's got a unit. It's actually got a unit of width there. And we're applying this load, and we're supporting it at the neutral axis. And kind of intuitively, when we load that little slice, it's going to bend like a framework, and we can model that with just a stiffness. Okay, so that's a stiffness of just one slice. Okay, and each of these slices are identical before we load it. They're all the same dimensions and thickness. And then we're going to model this situation like this, where we now replace each one of these slices with a little spring. So we have a spring per unit of length. And as we push down here, and we're kind of assuming we have like a little flexible rope there, we're going to distort a little region of the top of this, shown in gray right here. Okay. So now we're looking in this direction here. And what we see is this shape here. Let me get some of this shape here. And we're going to take it to be a half sine. Okay, so we're applying the load here, and we get a certain amount of deformation right there. So that's right here. But if we move a little bit away for example, right here, we'll get a little bit less deformation until finally we move so far away that we're out of the affected zone. We're kind of in this region here where it doesn't even know we're applying a point force. Okay, so now we can look at energy principles, and again, don't kind of freak out when you see the equation here. Basically, we just did a certain amount of work with this load, so that's this value here, and we stored that in deforming all the little springs over this region, and that's what this is. Okay, and from that we can get an equation for the local stiffness. Okay, so the local stiffness that we would measure for the whole structure as we push down is given by how stiff are each one of these individual slices, and then it has to do with the width of the plate that we're applying a load to. Okay. So here's an equation for how stiff is a slice. Okay, we're not developing this right now, we're just kind of stating it. And then when we put that into our equation, we end up with this relationship for the local stiffness. Okay, now this one is worth remembering. And you kind of went through the process that we went. So this big local stiffness is what we would measure if we applied a load to this section, and we would measure how much did it distort right under that load. Okay, so that's this value here. And again, the elements are kind of what we would expect. It's a function of Young's modulus. A higher Young's modulus, the higher this thickness. And it's a function of some of the dimensions of the section. Okay, so now we have a new model for our beam. We can still model it as a beam, and kind of an ideal beam. But on top of that, we have this local flexibility where we are distorting the section. And these are two springs in series. So we're pushing down here, and we're measuring not only the distortion of the beam itself, but we're also measuring the local distortion of the section. Of course, we don't want it, we would like this to be really stiff. So if that's really stiff, then all the flexibility is in the beam, just as we originally imagined it. Okay, and this equation, at least for rectangular sections, is the value for that K local. So let's go back to our little example of the van structure. So we went through and we had calculated the stiffness of the beam before, and we said that was really stiff. That was actually greater than the requirement. But now we realize that we have this local flexibility occurring, that we get some flexibility in just the section is kind of smushing underneath, and that value is given by this equation. So let's calculate how big this is for this case. Remember, we have the dimensions and the materials here. So here's the equation. H and B, they're both the same in this case. We have a square section. This is the thickness, and this is B, the width of the section. So this local flexibility in this case is 33.9 millimeters. Okay, so really very flexible compared to the beam. So this is what we had calculated before. So you see the big difference. And when these two springs are in series here, the most flexible one will dominate. So basically, all we're doing is smushing the section. We're hardly distorting the beam at all. Okay. So although the beam is sufficiently sized to meet the requirement, the local distortion dominates the deflection behavior. Okay, so we have these two values. So we can actually calculate what is the system stiffness of this. It's two beams or two springs in series. So if you remember from basic physics days, whenever we have this condition, then the equivalent single spring is equal to the product divided by the sum. So when we put these into this equation, we get the value that would have been measured if we had tested this. Okay, so one of the things we can calculate is saying, okay, well, the section will distort. It's a flexible section. We know the beam will provide this. So how stiff do we really need to be in order to meet the requirements? So before we saw if we do nothing for the point load application, this was down around 33. So how stiff does this need to be in order to meet the requirement of 1500? Okay, so what we are going to do is just solve this equation for K local. So again, we're just looking at two springs in series, and in this case, the reciprocal of the equivalent spring is the sum of the reciprocals. And we do a lot of algebra until finally we get a value for the local stiffness. So we're saying that we want the system stiffness to be the requirement. So every time we see system, we're going to put 1500. The beam stiffness here, 1570, and up here. And now we solve for local, and that means we have to have this value for the local stiffness. So you see, super rigid for the point of load application, 33,600 newtons per millimeter. So how can we get these kinds of values? So what physical ways can we do it? So here's just some strategies to get that high local stiffness. And here again, we're looking at kind of just a section of the beam. And this is the one where we have no treatment at all. We just have the really big plate at the top that's going to distort a lot. So here's the value that we got, 33.9. So here we're just going to say let's just take like a tube, and we'll put a tube all the way across the section from top to bottom where we're applying the load. And that does a lot. That gets us all the way up to 97, right? 3 times where we started, but a long ways from where we want to be. Here's another strategy. We're just going to put a really heavy doubler across the top. So if we were to look at this, here's the section. We're just going to put a really heavy doubler there and then push on that doubler. Okay, that gets us up to 23 or 2400. That's really a lot more. And then finally, here's if we put a bulkhead. So what we're talking about with a bulkhead is we're going to literally take that section and put a piece that goes right across there inside, and then we're going to push on that bulkhead. Okay, so this requires an internal piece, and now we're up to 82,000. Okay, so now we've come up with an adequate solution. Okay, so from right about here to the right side, we're really starting to improve the performance. And let's say, well, understand why. Why does this work? Why are we, going here an order of magnitude and then here another order of magnitude better? Okay, so let's see what's in action here. So here is a model of the beam here that we're just supporting on the ends. And here's the load that we're applying. Here we're showing it pulling up, it could be pushing down. And what we're kind of showing is a need that we somehow not load this very flexible plate here. We know that that's going to really distort. So how can we get the loads from this point out to the sidewalls of the plate? And that's the first principle here. We need this kind of a rigid little member here. So this is similar to this case with a doubler or some kind of a member that we push on that member, but ultimately it puts the loads out to the sidewalls of the plate. Okay, so that's number one. And now here's we're going to be looking at the sidewalls here. So here is the force that we're now applied to the sidewall. We need to distribute the loads to the shear members of the web. So here's the shear members in the front and the back that are really reacting the load. So the real takeaway here is somehow if we have a section like this, we don't want to just apply the load in the middle of a very kind of floppy plate. We need to have some kind of a member to get it out to the sides. And then once we're out to the sides, we're really reacting that load in shear, which is a very effective way to react loads. So let's look at some physical ways that that can be done. Here we just align the load. We kind of maybe, if we have the ability, we just move the load out to the side so that it lines up with the shear wall of the section. Here's the local reinforcement. You see here, maybe it's a little C-section on its side. So even though we're putting the load in the middle, we're reacting them at the shear walls, side walls of the section. Here's another way to do it with a bulkhead. So this goes from across the whole plate from one side to the other. We apply the load here, and the reaction ends up to be at the side walls. Okay. And the additional feature of a bulkhead is it forces the section to maintain its shape, in this case a rectangular shape, so we don't get any distortion occurring. Okay. And then the last way, not very desirable again, but if you're late in the design process and you can't really make any other changes, squirting some semi-rigid foam into the section will help mitigate that deformation. Okay, so these are the kind of the real strategies for having a good point of load application for a concentrated joint load rather. Okay, so here's a good example of that. What we're looking at is the pickup bed attachment. So we're attaching the pickup bed to the frame rails. Here's the frame rail. The pickup bed has some cross members, and then generally there's an attachment that attaches the cross member to the frame. Okay. We're looking at a solution for the Ford 150 and I guess it's the previous generation of the Silverado here. Okay. So we're looking at attachments here and here. Here's the cross member and then the attachments. Here's a cross member and then the attachment. Okay. So this area right in here for the Ford looks like this. Okay. So we're looking in this direction down the end of that cross member. Here's the cross member. We're going to put a point load in here where it attaches to the frame. But what they've added is a tube that goes from top to bottom in a doubler there. So you can kind of get the idea that as we apply a load here, it's reacted there and there, down the side walls. So in this is a section of the Chevrolet. So here again, we're looking in this direction. Here you see a little nut that holds things in place. You see a little bit of a reinforcement, but not as great. So the idea is that they're still trying to transfer the loads to the sidewall, but not quite as effectively as in this configuration. So how does that manifest itself? Here we're looking at the end view of the vehicle. Here's the frame rail sections. Here's that cross member we looked at, and we're considering this area here where we're bolting them together. Here the Ford has done something like this, and the Chevy version looks something like this. Okay, so that as we apply loads to the cross member, put weight into the bed, we get something more like a pin joint here. We have more flexibility here for the Chevy Silverado and more localized stresses. Okay, so that's an example of this idea of how do we adequately react a point load. Here's another kind of configuration here. We're looking at a section through the motor compartment, the mid-rail. We're going to put a powertrain mount here, and we know if we don't do something to the section, we'll have a lot of local motion there. So here is an example. This is from a Camry of a through the section reinforcement. So this really includes a lot of things. It's a very large load that comes in here. So you see here's a bulkhead here and here. So this is causing this cross section to maintain its shape so that it doesn't have gross distortion. Here is the point of load application, goes all the way through, and then here's where they're kind of transferring the loads to the sidewall. So here's one other example. This is from an experimental car. This was the ultralight steel auto body design, and we're looking at the hinge attachments for this particular car. When we have like a normal type hinge, here's the hinge pillar itself, so we're looking at a section like this. The attachment of the hinge can look like this. So it's hooks on here, and we're applying a large load here from the door. In that, as we apply that load, that can distort this section back and forth. Okay, so that's an example again of a point load coming into a thin wall section. And here's the design for this ultralight steel auto body. The hinge actually goes through the hinge pillar, so when we apply a large load like that, it's reacted right by the shear walls of the section directly. Okay, so not much distortion would be occurring as in this case. Okay, so really what we just covered today is the idea of spot welding and kind of some of the bad effects that it causes a structure. And we talked about this idea of whenever we have a point load coming into a thin wall beam, we really have to add a lot of reinforcement, very careful geometry in order to make sure that we get the true advantage of the big beam section as we load it. So where we're at now is kind of a milestone point in this course, is that we've been looking at body structural elements. Like you see here, we've looked at beams, spot welding, we looked at brackets, we looked at panels. So we have some understanding of structural element behavior. And now what we have to do is consider how to apply these elements, how to turn the beams and the panels into part of a body structure that's ultimately going to react or meet requirements for overall body bending, body torsion, and crashworthiness requirements. Okay. And just to give you a feeling for how we're going to do that, and we'll start on this in the next lecture, ultimately here's what we want to be able to do is have section and panel requirements. Okay? So if somebody came up to you and said, I'm designing a section for the B-pillar and I need a certain moment of inertia and I have a certain ultimate moment that I want a yield of the effective section, you would be able to take those requirements and start to design a section to meet them. But where do these requirements come from? And where they come from is from a flow down of requirements. Okay? And I'm going to just give you an example here. This isn't the only one that we'll be looking at, but this is one for body requirements. This is going to be the one that we start to look in the next lecture. So we start with the voice of the customer saying, something that they desire in the vehicle. Like in this case, they're saying that we want to have a nice solid feel as we drive down the road. Okay? So that's at a vehicle level. And we need to quantify that requirement. And an example of that, again, we'll be seeing in the next lecture, is that we want the primary vehicle frequencies, the bending frequencies, to be at least 22 hertz in order to meet this customer need. And then we're going to flow those down to another level, to the body structure system. So here we're at the kind of the body in white level. And for the case of body bending that we're looking at here, just an example, we'll have a certain stiffness that we need. If we meet the stiffness, then we will probably meet this requirement at the vehicle level. And then we can even keep flowing these down. Now we're going to look at the side frame of the car. There's a bunch of beams in that side frame. So if we have this requirement for the stiffness of the overall body in white, what does the side frame have to do? And then finally what we can do is from that flow those down even to the section level, like take the B-pillar and say, well, what does that have to do in order to meet this requirement, which meets that requirement, which meets that requirement, which meets the customer need. Okay, so we've looked at this as using body bending as an example. That will be the series of the next few lectures, and then we'll do the same for torsion and then for crashworthiness. So that's kind of where we're heading in the course here. So major kind of a break point here as we go from looking at the tinker toys that build up the structure to putting them all together to meet certain requirements. Okay, so with that, we'll call it a day, and we'll see you next time.